Hello everyone, this is Dr. Hopkins narrating the next video in which we describe Maxwell's relations. So we have these new free energy functions, the Helmholtz and Gibbs, and we can expand Helmholtz in terms of T and V and Gibbs in terms of P and T. Now they are exact differentials, and we can expand our differential equations in terms of our partial derivatives, right? So if we expand, this is what we derived in the previous video, but now this is partial A, partial T, this is partial A, partial V. Likewise for the Gibbs, we have the partial G with respect to P and partial G with respect to T related to this. And so what that means is that each of these, this is minus P, this one is V, and both of these partial derivatives are minus S. Okay. So we can use this idea that we have these exact differentials to relate kind of measurable partial derivatives, quantities, to those that aren't so easy to measure. So the Maxwell's relations, let's derive one of them. We'll start with the first, this internal energy from our first law. So it's du is T ds minus P dV we had before, so that was dq. Reversible, that's work reversible. Now we're restricting to PV only. And then we can also expand it in terms of the partial derivatives of u with respect to S and V, right? Which means this is equal to T, and this one is equal to minus pressure. Because it's an exact differential, we can then take the partial derivative of this partial derivative here, and that is equal to the partial derivative the other way. So we're evaluating V and S or S and V. It shouldn't matter. It is a state function, right? So that was our concept of an exact differential. And so if we do that, that means that we substitute in T for this one and P minus P for this one. We can relate the change in temperature with the change in volume at constant entropy is equal to this partial derivative here. So we've related something that is somewhat measurable, although with the constant entropy, it's a little bit tricky to set that up, to something that's a little bit more difficult to measure. And we can do one of these for every exact differential we've introduced in the course so far. And so if we look at this, we've got four of them. We've got du, dh, dA, and dg. All of these are expanding and relating them to the various quantities. And so you can see, because these two equal minus S, they're equal. These two equal T, they're equal, and so forth. So you have our four Maxwell's relations. And then I've expanded them to include the measurable quantities alpha and kappa as well. All right, but I'm not going to belabor all of these. You can look through these individually. And so let's see, what can we do with this? And actually, one of the reasons why we're kind of going back to this Maxwell's relations is back in first law, we had a derivation, or we used this equation for the du dv at constant t without a derivation, because it required Maxwell's relations, or second law and free energy, in order to derive it. So here we start with, so we're going to derive this quantity here. So we start with our definition. We're going to hold our temperature constant and evaluate how it changes with respect to volume. Okay, so we basically divide by dV at each one of these, and then that means this goes to 1 because that's dV over dV, right? And then if we were to go back to the previous page, the Maxwell's relations, so if we look at this one, this is something that's very difficult to measure, but it's related to this, which is actually quite easy to measure, right? So we can substitute that in, and we end up with the partial u with respect to v at constant t is this t times this partial derivative minus p. And for an ideal gas, that equals 0. And we also derive that for a van der Waals gas and so forth. But that's how we arrived at that quantity. We also did the same thing. We introduced dH/dP with respect to t, at constant t, in first law, but we never derived it. But you can imagine that you can use Maxwell's relations to derive this quantity. And I will leave that to you.